if you remember in the previous lecture or even all the lectures, that we always use a current source. And that current source, how do you generate, how do you make it available on chip, it's important, and that's what we're going to discuss today. So let's say this is a chip, okay, and you could potentially do this. You could have, maybe there is a transistor over here, there is a transistor over here on the other side of the chip, and these are different transistors on different sides of the chip. And then you could technically speaking, you could connect all the gates together coming out of the chip, and then you can bias all the transistors using an external voltage source. This is not such a good idea, and the reason for that is each one of these transistors, they are on a different location on the chip, and the transistor parameters, they change quite a lot from location to location on the chip. So you will not get exactly the same current that you were expecting from these this configuration. Also, there is something called a ground connection. This ground connection may be going to different locations on the chip, and there could be different resistance in that path. And if there is any IR drop in that ground path, then the amount of current will also change in each case. And this is not a very desirable situation. So don't do this. Basically, this is not a good way to bias your transistors and also create current sources. So how do you do that? And I'm going to show you what we do on most of our chips. Especially in the production level type of operation. You can get by with the configuration shown maybe in the lab and tweak each voltage source, but then it becomes, if you have 1000 transistors, it becomes totally gets out of hand. So maybe 4 or 5 transistors, you could probably tweak each voltage, but definitely not recommended. Okay. So the way generally you distribute currents on a chip is typically in one corner of the chip there is a block which will generate current references. Okay, so this is the block that generates current references. Okay, so the purpose of this block is to create current, and we are going to discuss that at later time. How do you generate these references? And so this is like, for example, in this case it's a PMOS transistor, and when everything is connected properly, it will give you different values of current. This will be IO1, this will be IO2, and things like that. What you would do then, instead of transporting voltage to different location on a chip, you would rather transport current, and it has certain added benefits. So which is what I'm going to show you. So here you could have a block on the other side of the chip, far away. You could have a block called current mirror, okay, which will just take that current and mirror it locally, and get you multiple copies of the current. Now keep in mind that the transistors match very well when they are laid out properly and they are next to each other. However, as soon as the distance between them starts increasing, then the matching between them gets worse. Okay, so that's the property that we need to keep in mind. So in this particular case, in this particular current mirror that you're seeing, let me erase this particular block here. This particular current mirror that we are seeing is, these transistors are next to each other. So we would get this current from, and this routing could be very complex depending on the layout. It could be, it could have a lot of resistance in kilo ohms type of range. However, the process still works because you're transporting current from one location to another. Current is like water. As long as the water doesn't leak through, you're okay, and it should reach in the other location, exactly the same value. And here you could have a different ground path, and that's okay, because finally it's a current which is traveling to the next stage. Okay, and you could have another current mirror on the bottom over here, which would have a bunch of matched transistors, so we can replicate the currents. And this particular path could be again long winding depending upon what comes in its way, and it eventually lands up here, and there could be different ground connection, ground 2 on the chip. Okay, so these two currents basically, once you design with a proper ratio, then IO1 and IO2 relationship should stay intact, and then locally these currents are mirrored over here, and they should match very well with each other. Okay, so for example, this would be IO1 that will flow here, and this will be IO2 that will flow over here. And this copies of IO1 and IO2 can be made locally and used in that particular circuit. And this particular method works very well on the chip because even with the physically they are far apart, you are able to faithfully replicate currents all over the chip. So the key block here is the current reference. How do you generate current reference? That we are going to address it later on this course. What in this particular lecture we're going to talk about is, hey, how do we do these current mirrors? How do we create these current mirrors? What are the properties which are essential for this current mirror? And then how do we design them? In this particular lecture, I would like to go with the MOS design first, and then later on we will switch to bipolar and contrast the two cases. Okay. So the key properties of the current source which are used for biasing. Okay, so you're going to use current sources for biasing. And what are the key properties? So key specifications are as follows. Most important one, you would think that, hey, how about the output resistance of the current source? Okay, so ideally what we want is output resistance to be infinite, as large as possible. So desired infinite because it's a current source. And then how about voltage compliance? What this means is if we show this as a current source, then no matter what this voltage at the terminal of the current source is, the current source value should not change. So how flexible you can be in terms of what the voltage value is there. Okay, so this is kind of gives you min to max, voltage range, which will give you current value up to certain accuracy. The next thing would be accuracy of your current source, and its process temperature and supply voltage dependence. One thing also we look for is input resistance of the current source. It's a current mirror, so we have to push some current in that block. So if the input resistance is high, then the previous stage's output resistance will matter, and we will talk about it at length a little bit later. So what we would like here is, because it's a current sink which is producing current source on the other side, for the sink portion of your current mirror, the input resistance should be as low as possible. Also, the other thing is DC balance of voltages. So these two properties, they are required for current mirrors. Rest are more for a standalone current source. So if you have a current mirror, then the input resistance is important because you are pushing some current into that current mirror to produce an output current source. Okay, and DC balancing, what that means is, inside the current mirror, you want the voltages across the devices to be matched properly, otherwise you will have effect of channel length modulation. The schematic of the current mirror looks like this. So we have a reference current coming in from somewhere. For example, a chip would have a master bias type of circuit which will generate current reference. So this current source that we are saying is coming from there. Or it could be that within the circuit you have generated a current source, a reference, and then you want to replicate it all over the place for various different circuits. So this would be that current source. Then what we do is we put it through a simple current mirror, which means a circuit that looks like this. Let me draw this completely. And so this would be your V out, and this would be your I out. Transistor M1 and M2, okay, these are the two transistors, and there is a gate to source voltage of VGS over here. So the current source, this is VDD. The current source I, or Iref, let's call it reference, it's coming from somewhere, and then we insert it into this diode connected device, VGS. When the current flows through the diode connected device, it will generate VGS, and that VGS we apply to the different transistor M2. Now these two transistors could have two different aspect ratios, W by L1 and this is W by L of 2. Okay, so let's figure out how this current mirror fares in terms of all the different parameters that we just talked about earlier. Okay, so the first thing, what is the R input, which is R in over here, and you can tell by inspection the R in is going to be equal to 1 divided by GM1 of the transistor plus GDS 1 of the transistor. So here again, you know, GDS is gate to drain to source conductance in a saturation region, which is same as our reciprocal of RO. Many times when you are dealing with conductances, and if there are two resistances are in parallel, then easy to analyze them as summation of two conductances. But when two resistances are in series, then we add the two resistances R1 plus R2. But if the two conductances are in parallel, then we can add the two conductances G1 and G2. So in this particular case, GM1, it's already there for transistor M1, and GDS1, which will be the output resistance, reciprocal of the output resistance. So we interchangeably use G and R to suit our convenience depending upon the configuration of the circuit. Okay, so this would be your R input, and what would be the let's see, the minimum output. Okay, V out minimum. We already know the transistor M2 is going to be in saturation region only when V out minimum is equal to VD sat of 2. Okay, so if the V out goes below VD sat 2, then transistor M2 will be out of saturation, and we won't get the current that we were desiring to get. If we plot the current as a function of V out, since we are analyzing, we are looking at M2 as a current source for other circuits. So if we plot, this is your I out, okay, versus V out. So ideally, what we would like to see is, hey, ideal current source looks like this, right? It should be all flat. It doesn't matter what V out is, I should always get I out. However, in this particular case, what we are going to get will look something like this, and you will see what I'm talking about here. I'm intentionally doing this. Okay, so then what you would get is, you would get a wave, the characteristics something like this. When V out is less than VD sat 2, the transistor M2 is going to be in non-saturation region, and from VD sat 2 onwards, it will be in a saturation region. Okay, so when your V out is equal to VGS 1, then we will get the desired current, which is whatever we required, you know, IREF. For example, if the ratio is 1:1, then you should get IREF. The channel length modulation has certain role to play here, and as a result of which you get this particular slope over here. So what we want ideally in a current source is the output resistance to be as high as possible, so that we can ignore the effect of channel length modulation. Okay, all right. So let's write a couple of equations and we'll get a lot more clear about it. So IREF is equal to, what is IREF for the transistor M1 is going to be mu n Cox W by L 1 of the transistor divided by 2 VGS minus VTH 1 of the transistor M1 square. And let's do a little more accurate analysis, because we are also looking at exactly the current source value. So it will be lambda 1 VGS1. This should be VDS1, which is equal to VGS1. That's why we have put that in there. Okay, all right. And then I out, output current is going to be mu n Cox W by L of transistor 2 divided by 2. And in this particular case also we have VGS is the gate to source voltage minus VTH2, which is the threshold voltage of transistor M2 square, multiplied by 1 plus lambda 2. Okay, all right. So we can assume, since these two transistors are M1 and M2 are right next to each other, you can assume that and also there is no body effect in this case. Both of them will have ground as their body. So we can assume that VTH1 is equal to VTH2. Okay, for the first order approximation. So in that case, if we look at the ratio, let's say I out divided by IREF, what would that be equal to? That would be, if you look at the overall factors, only thing which will be left out will be W by L of transistor 2 divided by W by L of transistor 1, and then you will have 1 plus lambda 2 V out divided by 1 plus lambda 1 VGS. We want mirroring to be predictable and accurate. If you choose the same length for both the devices, okay, then it kind of makes sense that you would get the same lambda, and it would be easier for us to replicate them. So for accurate mirroring, you can keep L1 equal to L2, which will give us lambda 1 equal to lambda 2, and let's say that's equal to lambda for a minute. Now this particular factor, the second order effect lambda times voltage, is a small factor, right? So then we can use our approximations, and you will see that I out divided by I ref will be equal to W2 divided by W1 times, I can make the approximation, lambda times V out minus VGS. Again, we want this effect to be as small as possible. You want lambda to be as small as possible so that we are independent of the output voltage, as a result of which we want channel length to be as high as possible. So keep your length, when you're mirroring current, channel length as high as possible compared to L minimum. So any technology, let's say you're using 1 micron technology, what that means, 1 micron CMOS technology means the channel length of that device is going to be, minimum channel length will be 1 micron. If you're using quarter micron technology, which is 0.25 micron technology, that means L is equal to 0.25 microns minimum. And what we have been using lately, the last chip that we did in our lab was 65 nanometer, which means that the minimum channel length is 65 nanometer. The next project we are working on is 40 nanometer technology, so which is the minimum channel length is 40 nanometers. And of course, if you look at the latest and greatest processors, they are going towards 1.4 nanometer, or maybe even lower than that. And of course, when you try to reduce the channel length, things get exponentially more expensive. If I ignore the lambda or keep lambda as small as possible by choosing large channel length, then we can see that, hey, I out divided by I ref is equal to W2 divided by W1. This would be our first approximation that we could get. So let's say that you want to get your current mirrored in such a way that, let's say your reference current is equal to 10 microamps, and I would like to mirror it to, I would like to get an I out or current source of, let's say, 100 microamps. Okay, then obviously what you would do then is you would do I out divided by I ref is equal to W2 divided by W1 is equal to 10, which means that W2 should be 10 times W1. This is very easy to do, correct? So then, you may think that, hey, that's pretty easy. I just have to choose 2 devices, with one device which will be a unit size device of W1. Let's say we choose W1 is equal to 1 micron for the sake of discussion. So let's say W1 is equal to 1 micron. Then I can just choose W2 equal to 10 micron. This would be the natural thinking. However, this doesn't work very well. And I'm going to explain this particular nuance, and hopefully you'll appreciate this as we go along. And this is kind of where the basic analog circuit design techniques come into play. You could draw the transistor. This would be your diffusion area. This is your poly, something like this. And this would be your transistor with 1 micron width. And this would be the W1 part. And then I could technically say, all right, so since I want ratio of 10, I would just take this W and I would make it 10 times larger. This would be, let's say, 10 microns. You may think you're done, but this is actually a bad practice. And let me explain why. If you just look at it, the definition of the gate is done using a lithographic technique. So even when you say you have W and L, you always get W plus delta W, that's the error, and L plus delta L. So for example, for 1 micron, this delta W could be maybe few percent Okay, and for let's say in this case the channel length is, let's say in this particular example, let's pick a number, maybe 100 nanometer. Okay, and you would get maybe 10% of that. This would be the variation. Now this plus sign doesn't have a meaning. It's a random variable depending upon how the transistor is drawn. So you can quickly see that when I do, and this part comes in because if you magnify this particular portion, let's say, let me draw a picture here. Let's say we just magnify the gate portion of this transistor over here. Okay, then it's going to look something like this. The edges are going to be little bit, you will have some kind of effect, and this is all due to the lithography techniques. So you would see, the W actually is W plus minus, actually not plus minus, let's say delta W, where delta W can be negative, and here is your channel length L, which could be L plus delta L. This is the uncertainty. Delta W and delta L are uncertainty in your transistor size. So when you do the 10 micron device, you're going to get, effectively what you'll get is again 10 W plus delta W divided by L plus delta L. Now you can quickly see that if you take a ratio of these two, it may not be exactly 10, because in one side you have delta W coming into W, and then on this side you have delta W coming in with 10 W, because this delta W will only change wherever it occurs. So in this particular case, these are the two locations, edges, where you will see some delta W, and the same thing will be true over here on these two locations over here. So these two transistors will not match in reality on a chip. So there is a better way to do it, which is what I'm going to show you, and then you can quickly see how to match two transistors. And basically when you're doing analog circuit design, this is the fundamental principle you will be using day in and day out. So you are trying to match devices on a chip so that the result is more predictable. Okay. So a better way to do this would be, you have a single transistor, okay, and then you have 10 other transistors which are I'm not going to draw them right now. So you will keep doing this 10x times, and you will have 10 transistors. So what that would do is that you have, this is your M1, and this would be your M2 1 to M2 10. So I have 10 more transistors to get this replication effect by factor of 10. So in this particular case, your M1 will have W plus delta W divided by L plus delta L. Whereas if you look at the cumulative effect of 1 to 10, then you will also have 10 times W plus 10 times delta W divided by L plus delta. Okay, so this way I can get much better ratio, accurate ratio of factor of 10 when you desire to get a certain ratio. Okay, so then let's take another example. Let's say I have a reference current of 20 microamps. Okay, and this is our VDD, and so this example will make it lot clearer to you. And let's say I would like to replicate it by factor of 3, and this is what it would look like. So this is my M1 and this is my M2. So then let's say for some reason, due to some other analysis, we have figured out that W by L should be 5 microns by 1 micron, okay, due to other considerations. So now you could be tempted to just make single transistors of 15 micron by 1 micron. And what we discussed just now is this is not a good idea, because the transistor M1 and M2 will not match very well with each other. So instead what you would like to do is the following. What you would do is you would make this transistor and you would replicate this transistor 3 times like this, and then you would connect everything together. So you have 3 transistors of 5 micron by 1 micron, and this is also 5 micron by 1 micron. The combined current will be 3 times higher, and it would be predictably so of value 60 microamps, 20 microamps and 20 microamps. And these 3 transistors, which are identical replica of the original transistor M1, it will give us the exact factor of 3 in this particular case. Okay. The key thing that I'm trying to drive home here is when you go to integrated circuits, you would like to operate with unit cells. So let's say you want to match one transistor with another transistor, then you would like to figure out a common factor, and then you make that common factor as a unit cell and you replicate it as many times so that all the transistors behave the same way and you get the desired ratio. Okay, so one simple example, let's say I have a reference current of 10 microamps, okay, coming from somewhere, and then I would like to reproduce maybe, let's pick 22.5 microamps for some reason, right? So then here, by inspection, you could quickly tell that what is the common factor? So you can see the common factor is 2.5 microamps. I can make one transistor unit which will carry 2.5 microamps, and in this particular case this will be 4 units of 2.5 microamps of current, and then here it would be 9 units of 2.5 microamps. Okay. So 10 microamps is 4, another 10 microamps is 4, so 4 plus 4 plus 1, so that would be 9 units. Okay. So then what I would do is I would create a current mirror in such a way that this would have 4x, meaning 4 units, and this would have 9x, okay, meaning 9 units. So then if there is a 10 microamps of current flowing here, then it would be exactly replicated to 22.5 microamps. Okay, so this particular concept you really need to internalize, as if you are planning to be an analog designer, and you need to really learn how to match transistors. So this is like a 101 in matching in terms of unit cells. Okay, all right. So one other nuance I would like to tell you when it comes to analog design is specifically on when you are doing integrated circuit designs, is a layout aspect of how do you draw the transistors. So in the previous example, when I showed you that you would have, let's say you won't like to get a factor of 10 or factor of 2.5 or whatever factor, right? So then you would drop a single unit cell transistor and then you would make multiple copies of it. Now, if you keep doing that, then many times it's not very practical, because what happens is that these transistors need to be separated from each other. So there is a important concept when it comes to analog layout of the transistors, and it's called number of fingers versus effect of multiplier. So that's what I'm going to tell you about. When you draw a transistor, the green part is the source and drain area, and then let's say this is our so this is showing you a transistor that looks like this. Let's say this is drain of the transistor, and this is source, and obviously the gate is on this side. So this would be your gate, this would be the drain region, and this would be your source region. This is the way you will lay out the transistor. Now if I had to draw 10 more transistors, then what you would end up doing is you would end up drawing these transistors, like this, many of them, and then there is always a spacing that you need to keep between the transistors so that you don't violate any rules in the layout. However, so when you draw the transistor this way, let's say you did it this way, this is called multiplier. Okay, so when you write the transistor's size, let's say it's 5 micron by 100 nanometer, and then you would say multiplier is equal to 3 in this particular case, because we have 3 transistors. Now, there is a way you can do the same effect, have the same effect by combining the transistors together if they share the source and drain regions, and a good way to do that would look like this. So for example, this would be a transistor, so you would draw 3 gates, and then I would do a diffusion on top like this. So now I am sharing these the drain and source region areas in between the 2 transistors. So let's say if this was a drain area, then this would become a combined source area, this would be drain area, and this would be source area. So when you put metallization, what you would do is you would combine this and this region, you would combine this and this region, and of course you would connect all the gates together, and this now would be represented as one transistor with since we have 3 transistors, it would look like 15 microns by 100 nanometer, and this would be number of fingers is equal to 3, because fingers is the gate gate regions that we are defining. And what this effectively means is you have 3 transistors of 5 microns by 100 nanometer, and you have 3 fingers, and the drain and source regions are alternate and they're shared. So this would in effect reduce the area of the transistor, and you can that way compress more devices in the same region. So this is another nuance. So what you learned right now is there are 2 ways to draw transistors. One of them is the multiplier. When you do the design in a software, Cadence or any other software, right? So there are 2 choices that you have. One of them is a multiplier choice, or you have number of fingers choice. And this is what it means when it comes to it. So you can choose multiplier equal to whatever n, or you can choose number of fingers is equal to n. So number of fingers equal to n means that you have transistors with n number of gates. They're right next to each other, and the drain and source regions are shared, as I have shown in the right side. And then if you have multiplier n, that means you just stamp that transistor n number of times. So it's obvious that if you stamp the transistor n number of times, then that would give you the perfect best possible matching that you could get, because each transistor would look alike. The next best thing would be having number of fingers, NF. So these are the alternatives where you have one transistor of 5 micron and the second transistor of 15 micron, elongated. So that would not match at all very well. All right. So let's move on to the next current mirror. So we learned about simple current mirror and how do you size the devices when you would like to get scaled copies of the current mirrors. Now the next current mirror I'm going to teach you about is called Cascode current mirror. So in the Cascode current mirror, we already learned what Cascode means. You have one device, and on top of that you put another device with a bias voltage and keep everything in saturation, and we call that configuration as Cascode transistor. It would look like this. I'm just going to draw the schematic for you. Now here, let's see what's going on. So first of all, let's figure out what's our input out here and what's our output here. Okay. So what is our input? The R input, let's label the nodes. This is node X and this is node Y, and I'm going to label this node as Z. Okay. So we have 3 nodes in the circuit, and other than the output node. And if you look in this particular node, it will look like 1 divided by GM1. I'm ignoring the output conductance of the transistor, which is GDS1 or Rout that we call, right? So and then there is another transistor on top, which is another 1 over GM3. So if the 2 GMs are alike, then your R in resistance, you have 2 resistances in series, so you get 1 over GM1 plus 1 over GM3, and this will look like 2 divided by, and if you look at the Rout, what would Rout look like? So if you remember, we learned in the last lecture, a couple of lectures down, Rout looks like you have a source degenerated transistor, and if this was R and if this has GM and Rout, this transistor, then when you look at it from the top, what do we see? We see this R getting multiplied by the gain of the transistor GM Rout. Okay, this is what we would see, and this is something that we learned earlier, so we could use that principle over here. Now in this particular case, what is the Rout looking down at node Z? That will be equal to RO2, and that will get multiplied by the GM4 R4 Rout 4 of the transistor M4. Okay, so you would see something like, so Rout will look approximately like GM4 RO4, which is the gain of the transistor M4 multiplied by RO2. So we can see that now the gain, the output resistance has increased by this factor GM4 RO4, which could be 20, 50, something like that. So we have really increased the output resistance of this current source, and which is what we want. We want R out to be as high as possible. This particular current source, the Cascode current mirror or current source, has a benefit that it has a higher output. Now let's analyze what's the lowest output voltage V out that you can tolerate so that both the transistors M2 and M4 are in saturation. Okay, so I'll mislead you first. A typical answer could be, hey, it could be just VD-SAT 2 plus VD-SAT 4. That would be your, if you remember, shoot from the hip answer, right? So you would think that the minimum V out can be VD-SAT 2 plus VD-SAT 4, which is equal to, let's say, approximately 2 VD-SAT. But that is really not the case. So follow this train of thought to understand what's really going on here. So what is the node Vy, by the way? If you look at node Vy, which is this node, what is the value, the voltage at this node Vy? That is, node Vy. That would be VGS1, which would be something like VTH plus VDSAT, something of that order, right? Now, what is node Vx? The node Vx, which is this one, that would look like VGS1 plus VGS3. You have plus minus VGS1 and then plus minus VGS3. So what would that look like? So that let's write that up. That would look like, so this is what Vx is, and let's figure out what node Vz is. So Vz is going to look like Vx, which is this particular node, and then we are going down by VGS4. So Vx minus VGS4. I think this is the key revelation that you would see. Let me repeat this again. At node Y, which is marked over here, you have VGS1. At node X, you have VGS1 plus VGS3. And when you go to node Z, which is over here, you will see VGS1 plus VGS3 minus VGS4. Okay, because you have to go down from this to this by VGS4. This would look like VGS1 plus VGS3 minus VGS4. Since everything is matched, VGS3 and VGS4 should be identical. Also, VGS1 and VGS2 should be identical. So, since VGS3 and VGS4 are identical, they will go away. And what you will notice is VZ, which is this node in the middle, that would be equal to, what will be the VZ equal to? VZ will be equal to VGS. So that's no matter what, if this current mirror is carrying current IRef, then VZ is going to be equal to VGS1, just because of the Kirchhoff's voltage law around this loop, right? Okay. Now, to keep the transistor M4 in saturation, what's the smallest V out that we can have over here is you will have VD-SAT 4 across the transistor M4. So if you look at V out, that will be equal to VZ plus VD-SAT 4. This has to be clear. So if this is VZ is the node, you will have you have, because of the mirroring action in the Cascode current mirror, VZ will be always VGS1 because symmetry there. And then on top of that, the transistor M4, the V out can be lowered only to the point that M4 is still stays in saturation. What that means is that the VDS across M4 should be, minimum would be VD-SAT 4. Okay. So then we can calculate V out. V out will be, what is VZ? Again, that's VGS1 plus VD-SAT 4. Now VGS1 we said is equal to VT plus VD-SAT, and VD-SAT 4 also we can write at VD-SAT. So then kind of ballpark number, it will look like VT plus 2 VD-SAT. The reason I'm kind of assuming all transistors have equal VD-SAT is it becomes easy to figure out what would be the voltage level in a ballpark number, because we kind of know by design we like to keep VD-SAT equal to maybe 150 millivolts to 200 millivolts. So that way also we know VT is, let's say, 500 millivolts. So we can quickly calculate what the numbers are. Okay, so all right. So then in this particular case, let's say if Vt is equal to, let's use the Vth to be consistent. Vth is going to be equal to, in this particular case, let's say it's 500 millivolts for NMOS device. The Vout is going to be equal to 500 millivolts plus, let's say, 2 times, if I keep 200 millivolts as a VDSAT by design, then this will look like almost like 900 millivolts or 0.9 millivolts, 0.9 volts. Okay, so you can tell the output voltage of the cascoded current mirror, you cannot really take it down that low. You have to leave at least 900 millivolts or 0.9 volts, kind of headroom across these two transistors to keep everything is in saturation. So you have a benefit of getting this gain of, in your Rout output resistance, the headroom or the amount of voltage you have to keep across these two transistors to keep them in saturation is is Vt plus 2 VDSAT, which can come out close to 900 millivolts. So this particular current source or current mirror is not very suitable for low voltage operation. What does low voltage operation mean? Low voltage means 1.2 volts, because if you're operating using 1.2 volts, then now you're left with barely 300 millivolts to play with. That's what I mean. And generally what has happened in analog design space is, you start with one idea, then somebody tries to improve it. So they improve one particular parameter, but then there is some disadvantage that shows up. The next person who comes in, they will improve further on that, and they will try to fix it, but then there will be yet another problem. And the evolution of design continues. So I'm trying to tell you the story in the same fashion. We started with a simple current mirror, now it's a cascode current mirror, and now we'll go to the next current mirror. So there are many such examples. If you dive deep into analog design, you can really study that and enjoy how the progression happened in terms of inventions. Okay, here is something interesting for you. So if you plot I out on the y-axis and if you plot V out on the x-axis, okay, what you would see in case of the cascode current mirror is the following. So initially when V out equal to 0, then you would get 0 current, of course, because there is no voltage across the two devices. And in the beginning, of course, you can see that if V out equal to 0, then M4 and M2 both are in non-saturation region or triode region. And then as you start increasing the V out, what you will see is current will increase, and then you will see something like this, and then you will see flattened region. Now let me explain what this means. So in the first region right here, so this would be VDSAT and this would be VT plus 2 VDSAT, something like that. In the first region, which is, let me use a different color here, let me use a green color. This particular region is one region, and then the red part is another region, okay, and then the rest. So beyond this, what you will see is the output resistance of the current source is pretty good. And you kind of get near ideal behavior, which is no matter what the voltage is, you will get the same current, okay, because the output resistance is very good. So you can pretty much tell that M2 and M4 are both in saturation. Below VDSAT1 or this VDSAT value, what happens is the transistor M2 and M4 both are in non-saturation. And in between this region, you will see transistor M2 will be saturation region, and the transistor M4 will be non-saturation. So this is an interesting way how this cascode current mirror works, and you can analyze it by using actual voltages and convince yourself that this is what is going on.